So tonight we have three very interesting talks. And first one here is Joel, who happens to be an old friend of mine. Since way back, we used to sit out in the woods and program with you and your four brothers, and learn the ins and outs of computers. And with that kind of background, you can reach to where we both are today. Welcome, Joel, and have a nice time.
Thank you, Johannes. It's really great to be here. Thank you so much for hosting me, Johannes and Johan. We've been talking for some time about trying to arrange this. I'm really excited to be here. Big thanks to Johannes as well, who actually was the one getting me really interested in computers and hardware and Unix and Linux and everything that's sort of got me working with what I do today. So thank you for that as well. I'm going to talk a bit about what we do at Facebook, where I work up in Luleå, where we have one of our data centers. I'm the site manager up there, so responsible for the day-to-day operations of the site. So I'll walk you through some of the stuff related to how we choose a site for a data center, some of the pretty unique technology powering the Facebook data centers, and some of the efficiency gains we get at scale running our data centers. I'll try to do questions at the end as well, and just a caveat there, I can hopefully answer loads of questions around data centers, our Open Compute project I'll talk a bit about in a few minutes, and what we do in Luleå. I'm probably not the guy to tell you details around how Oculus works in detail, or how the newsfeed ranking works, or the inner details of free-range lasers from UAVs that we're developing, anything like that. So apologies for that, but I'll try to answer questions around those topics at least. So a few numbers to just put what we do a little bit into perspective. Sorry. Is that better? Okay. And please shout out if you can't hear, or if anything is heard, right? These numbers we have to change them every time. Facebook is very quickly growing. We're currently at about 1.79 billion people using Facebook on a monthly basis. And out of those, about 1.1 billion are coming back on any given day. So our infrastructure needs to scale to be able to support that. And just some very big numbers there as well on the size of the platform. Like there's about 2 billion photos shared across our different services on any given day, and roughly 60 billion messages sent across Facebook and WhatsApp and our other services on a normal day. Those are enormous numbers. If you try to translate them into sort of metrics here and now, that's about 700,000 messages per second right now that's being sent through Facebook's infrastructure, for about 25,000 photos that's uploaded for every second right now. So our infrastructure needs to be really big to support that. Why did we choose Luleå to build a data center then? The cold climate is an obvious one. We have an average temperature of about 2 degrees Celsius, not written in the tourist brochures, but it's ideal for data centers. And as I'll talk about in a bit as well, we rely on free air cooling, which is even more efficient in that type of climate. We have extensive fiber infrastructure in Sweden in general, and definitely in Luleå as well, that allows us to connect the data center of this size, which was obviously a key thing as well. You don't want to have to build hundreds of kilometers of fiber optical cables to connect the building. We have an extremely reliable power grid in northern Sweden. We have not had an outage since the early 1970s, and we are connected to 2 completely separate power grids that intersect where our data center site is, which then actually allowed us to rely on the whole power grid for redundancy instead of having backup generators. So with that alone, we could cut the number of backup generators with 70%, which is obviously a big environmental saving and also allows us to build the sites in a quicker fashion. Access to renewable energy, this is huge for us. Luleå was our first data center site that was 100% powered by renewable energy coming from the Luleå River. And since then, each Facebook site built has been powered by renewable energy to 100%. Finding a site like Luleå where that was available in abundance was obviously key as well. Transportation infrastructure, we ship a lot of gear to our site to be able to turn up the buildings with servers, network equipment, and power equipment and all this, and that obviously requires a lot of good transportation infrastructure. local knowledge and competence. We have a big technical university in Luleå. You see commercials for them all over Uppsala right now. They've been growing very, very quickly. That's obviously key as well. Like, we need to have an ecosystem of skilled companies around us as well to be able to support us with the type of services that we need to run a data center and build one as well. And last but definitely not least, the local commitment and involvement from the municipality, regional government, Swedish national government, and lots of other organizations and people involved that made us, as a foreign company coming to Sweden, really, really feel welcomed and gave us really excellent support trying to figure out how to best get a data center built. So what do we have in Luleå then? Well, we have these two buildings right now. The one to the left here is unfortunately a rendering, but that's pretty much what it looks like. The first one to your right there, sorry, to my right, to your left, was started building in 2011, and we started serving traffic in June 2013. Then the second building here, with a different form factor but roughly the same size, was construction started roughly in 2014 and started serving traffic about 1.5 years later after that. And each of these are about 30,000 square meters in size, so that's a big number, right? But to put that in some perspective, if you think in ice hockey rinks, which we love in Luleå, like ice hockey is bigger than everything in Luleå, that equals to about 35 ice hockey rinks. If you prefer to compare to football pitches, that's about 12 football pitches big. Or for any Americans in the audience, it's about 2 aircraft carriers in size. Roughly the same. Actually, it's quite funny. The first building in particular is almost exactly the same length, width, and height as an aircraft carrier. Probably won't float. And this will be a little bit of a theme as well throughout my talk here. So the Open Compute project is something Facebook started, I think 4 years ago roughly, which is at the time a really unique initiative where we decided to open source all our hardware technology. Like, we come from a really proud and strong hacker background. Like, that's how our entire company functions and really is a core feature of our whole culture. And we just couldn't understand why the same open source philosophy that we saw in the open source world and that we heavily contributed. We're the second largest contributor to open source projects in the world right now, after Microsoft, interestingly. I didn't see that one coming a couple years back. We just couldn't understand why this didn't apply to hardware as well. We decided to basically open source all our hardware, being strong believers in collaboration, and this has just gone, I mean, way beyond what we would have ever hoped for. Today there are hundreds of companies and organizations being part of the Open Compute project, and while it started with Facebook technology exclusively, the majority of the technology today is actually developed by other companies. I mean, some of the really big names part of the project would be Intel, Apple, Google joined last year, Rackspace. There's a whole bunch of really, really big companies across the world, and also some academical users like CERN, for example, is looking at Open Compute, and a couple of others. And Luleå was the first ever data center we built that was 100% Open Compute, and since then that has been the standard as well. So let's look a couple of years back at what our infrastructure used to look like. Pretty much like any standard data center. We used leased data center facilities, standard colocation sites. We ran on standard OEM servers and network equipment. We ran pretty much standard PHP, Memcache, MySQL, and all these sort of other standard building blocks of any large-scale web company. And all of this really worked well, but it was also getting increasingly difficult to scale. And with the extreme growth we've seen, like this just wouldn't work. That this would have been a huge, huge bottleneck for us. So we had to start rethinking everything. And this is just one fun example of that. This is a 2 AM drawing on a napkin, actual sort of initial design of the entire electrical system powering our data center, which was a huge step forward in efficiency. That's something that we then, in pretty short period of time, actually started translating into a real world usage when we started building our own first data center in Prineville, Oregon. This was back in 2010. And from then to now, we've actually then built a complete data center ecosystem where we've gone from that first initial building that was at the time really, I mean, beyond what anyone thought was possible from an efficiency and cooling point of view, which I'll talk about in a bit as well, to today actually having, I think we're at 8 sites or buildings of this size today, and 16 in total in a relatively near future. So it's really grown into a massive data center ecosystem that Luleå is a big part of then, of course. And to walk you through a little bit around how this actually works and why was this unique at the time. Others have since started adapting this as well, thanks to the Open Compute project then, but it really relies on trying to make cooling in particular as simple and as efficient as possible. If you look in a traditional data center, it's often cooled by extremely power-hungry technology that's essentially the same as you see in a fridge or air conditioning unit. We realized that the outside air is perfectly fine for cooling most times of the year. So what we do is we take in, see if the laser works here, yeah. Outside air here that we mix with hot return air from the data halls to get the right temperature and not have to build up too much pressure. We take that through a series of filters, get rid of dust, pollen, insects, anything you don't want inside the data center. Once you get it in, you won't get it out, and it decreases the efficiency. Then what we call a misting system, which injects a fine water mist into the air, which we do for two reasons. It's our only way of actually cooling the air if we ever need to do that, which happens beyond 29.4 degrees Celsius, which in Luleå is pretty much unheard of, so not much of a problem with that. In other data center sites, it's something we rely on quite heavily though. We, for example, have a site in North Carolina where we had the second hottest summer on record a couple of years back. And despite that, we could rely exclusively on this technology to cool the whole site the entire summer. So it's just a fine water mist that's injected into the air. The other reason is to add humidity during winter. It gets really, really dry, especially in Luleå. So this is something we need to do then to get humidity up so you don't get problems with static electric discharge and these kind of things. Then we have a fan wall that drives the whole circulation through the building. Essentially, the whole building functions as one big server. From a cooling perspective. Instead of each little server having a small plastic fan cooling individual components, the entire building cools everything running inside it. That is then pushed down into the actual data halls. Only way out of there is going through the servers, picking up the heat, and then the hot air rises up to what we call the return air plenum to either recirculate back or go up here to be exhausted out to the building. Depending on time of the year, the proportions of air being recycled or exhausted varies, but during winter in particular, pretty much all the air is being recirculated. So it's an incredibly efficient building. One of the most common metrics in the data center world is talking about what we call PUE, which is basically the total amount of energy going into a building compared to how much of that is actually used to power or to run the actual servers and network equipment and other things that the building is meant for. And the lower or the closer you get to the theoretical limit of 1, the better. So a typical data center in the industry runs of a PV of around 1.9. So almost half of the energy is lost to cooling in particular and other losses throughout the building. Whereas the Facebook data centers have an average PV that roughly translates to 1.07, which is, I mean, beyond what you see anyone being able to demonstrate in the industry. And this is really thanks to a lot of different factors, but the cooling system is obviously one of them. And we're also trying to be as open as we possibly can around these numbers in a real-time basis. You can actually go into our Facebook pages and for each data center and see how we're actually tracking and trending right now. The numbers might vary a bit day by day depending on load in the building, environmental factors and so on, but you should on a yearly basis see roughly those numbers that I mentioned previously. And another metric, just to give you some sense of how much energy it actually takes to run Facebook, like powering the communication and collaboration of almost 1.8 billion people obviously takes a lot of infrastructure. But if all of those people were to call each other, send emails to each other, try to collaborate in some other form, it would probably be, I mean, a factor that's much higher than what we currently have. So right now, each average Facebook user using Facebook for a whole year roughly translates to the amount of energy required to make one medium-sized cafe latte. So that's the entire power footprint for a whole year then. Apparently it's the milk that's the big thing in this. The coffee is apparently not too energy intensive at all. So that's the data center side of it. Then we started looking at the servers, and I mean, you can buy servers from lots of different manufacturers, and they all have one thing in common, this that they are pretty much a one-size-fits-all. They try to cater for any potential use, so they have lots and lots of components that you don't really need probably for your particular use case. And at our scale, any type of efficiency gain that we can make, we really want to try to do it. If we can do something that's just 1% more efficient, we're absolutely going to try to do that. Because at our scale, that really will mean big numbers in terms of lower energy usage. So we started developing our own server infrastructure as well. You see a couple of generations of it here. The very, very first one being Freedom. That was back when we launched our Pineville Data Center in 2010. And then through a series of steps, we tried to make these designs denser and denser. And again, these are all completely open source through the Open Compute project then. So you can download the specifications, drawings, look at the patterns, all of this for all of this technology. And build your own if you want that. If you have the manufacturing capabilities. We have some later generation now, making them even denser. This is what we call Yosemite, which is actually 4 servers squeezed into one single unit compared to the previous one. So this allows us to build extremely dense compute systems with a very, very high number of servers per rack. And these have a couple of interesting features. They, for example, need a shared network interface to be able to communicate. 4 different servers share one network interface, a 40 gig uplink. And there's some really interesting technology behind how all of this works. So we've gone from basically building that first server, Freedom server, which was very much an experiment. We learned a ton of stuff along the way. And today we're at this, we're basically able to build our own complete hardware ecosystem as well. We build all our hardware ourselves, or design all our hardware ourselves, we don't necessarily build it ourselves. But since all of this is open sourced and through Open Compute, anyone that's interested in building these can of course do so. And that includes all the storage systems, everything basically that powers Facebook. And some of the early numbers here, moving to Open Compute from the previous generation, is that it actually allowed us to be 38% more power efficient at a 24% lower cost. And I'll get back to some of the cost aspects later as well. So this is just another way of illustrating the development we had over the years. We've not only built servers, we also built our own UPS systems, or battery cabinets. We started building our own NICs, we started building our own storage systems. We even started building entire storage systems that are integrated into one rack. These reach an absolutely phenomenal storage density of around 2 petabytes per rack at 2 kW, which is, really unheard of. A lot of that comes from some really, really clever algorithms to actually figure out how to store the data as well. So that's on the server side. But then we last year decided to do something really radical around the next part in the infrastructure that we hadn't actually done anything about previously, which is a network. So we decided to do a whole bunch of different things, or rather release a whole bunch of things that we've been working on for some time. Our own complete network hardware architecture, and our own fabric network, FBOSS, which is the software that powers our network equipment, and Sixpack, which is a larger switch than built on the same technology. And these are really sort of rethinking how network hardware works as well. If you think of a server and a network switch, the difference is not all that big. It's just that a switch has loads of ports. Apart from that, they function in a very similar way. And we really want to automate everything, and relying on proprietary software and proprietary hardware to do the network architecture was really, really cumbersome. It made automation really difficult. So we decided to build our own completely modular open source switch as well. That is essentially a standard microserver with redundant power supplies and lots of network cards. And this one has a 40 gig backplane, but sort of subsequent versions are higher capacity as well. We named it Wedge. I don't know who comes up with all the names, but this one in particular is named Wedge. Then we coupled that with software that we call FBOSS, which is not an operating system for switches. We run Linux on all our switches, as we do on all our servers to standardize things. Again, the switch shouldn't be anything different from the server. But FBOSS is really the software layer that runs on top of that to allow us to automate these at scale. And instead of having command line interfaces, for example, we just basically provide Thrift APIs to automate the switches. Because at our scale, managing things individually, logging into the individual switch to troubleshoot something doesn't work. We have to be able to automate all the troubleshooting and maintenance as well. And then Sixpack was essentially then the same technology at a much, much bigger scale with a very high performance backplane, and the first building block to actually do the last part of the network then to connect the different racks with the wedge top rack switches. So that's the network side of it that we really more or less completely decided to re-engineer ourselves as well. Last piece then, I could probably go on for hours about this one, but just to give a couple of examples of some of the software sides of this as well. Doing all of these hardware improvements is obviously really beneficial, but the really big gains comes on the software side, where we had some absolutely tremendous performance gain from things like HHVM or Hip Hop Virtual Machine, which has allowed us to actually squeeze out 5 times more efficiency out of each server compared to running standard PHP. And all our web front end runs on PHP, so I mean, I can't say how many servers that is, but it's a lot. And having to buy 5 times more servers, that would have just killed us. So this has been a huge, huge thing, which obviously then of course open sourced. On MySQL, which is one of our main databases, we've actually managed to lower the storage footprint by up to 60% and have 2 times less servers then, which is again then a massive, massive improvement cost-wise. And web-scale SQL, it's something that we teamed up with a bunch of other large internet companies to do to really try to adapt MySQL for large-scale internet deployments, and has been a big success as well. So what we essentially do is that we optimize the full stack. We build our own data centers, we build our own servers and storage to run on top of that. We connect all that with our own network equipment, and we run our own software on that, and then open source this whole stack as well. And why does this matter then? Like, isn't this a whole lot of work for doing something that you could basically buy off the shelf anyway? And yeah, there are some savings, but is it really worth it? If we look at the amount of savings Facebook has done since we started this work a couple of years back, it does save us about $2 billion US. So I'm not sure about the current exchange rate, but that's probably somewhere around 15 billion SEK in savings on hardware that we otherwise would have had to buy if we had not done all these things. So it absolutely pays off, and the same gains obviously something that translates into other organizations that leverage this technology as well.
Is that across Facebook or just in yours?
This is only Facebook.
That's all Facebook?
Yes. So, what it has done at other companies, we don't really know. Some of them tells us that
it was in your site in Lund.
No, sorry, yes. No, this is Facebook in total. So, what we essentially do then at Facebook to leverage all of this is that we treat our data centers as big digital factories where we really try to automate absolutely everything. Again, at our scale, we can't manually troubleshoot things. It's just too big to do that. So we try to automate as much as we possibly can. And things like repairing servers, for example, we do that in a very, very automated fashion where everything is properly pre-diagnosed. The technician knows exactly what's wrong with the server before he or she even goes there. We can actually automatically repair the majority of the problems happening on servers. Installations are more or less completely automatic as well. We roll big racks into place, connect network and power, flip them on, and from there onwards they take care of themselves more or less automatically, depending on where we put them in the data hall, our provision with operating systems and all this. Monitoring and everything associated with that is also completely automated. We cover that with a lot of thinking that you probably see in large manufacturing sites. If you go to a car manufacturing plant, for example, you would see a lot of similar logistics thinking as we would employ in our data centers, where we try to make sure we have the right amount of spare parts. You don't want to stock too much of it, but you'd never ever want to run out of a spare part that might have lead times of weeks or even months in some cases. So we really try to make sure we automate all of that. And again, that's not something that you can have the individual person trying to sit and figure out for lots and lots of different components. We actually have to automate all of that as well. And everything in how we turn up a data center and manage the capacity and build the servers and everything else is also highly automated as well from a logistical point of view. We have really industrial building automation as well. A building the size of ours, you can't manually manage that either. You need a system that runs the building automatically, factoring in outside air temperature, humidity, power load, all the different components that you need to automatically calculate the maximum efficiency of running the building. And we have a really extensive support infrastructure around us with big reinforcements of the power grid, fiber infrastructure, water infrastructure, roads, all of this that actually is required to build a site and run it in a very efficient way. And we really see the whole thing then as a big digital factory. It's a very, very clean one compared to most factories, but the same processes and same thinking that you would see in most manufacturing plants apply. And what does this done to us then in terms of numbers? Well, if we look at some of the metrics we like to track, this is one of them, the amount of servers each individual technician can look after. Well, back in 2009, before we started Open Compute and before we started building our own data centers, we were at about 5,000 servers per technician, which I mean is a really good number. But through lots of work with the automation and efficiency around processes, and definitely around designing and running our own hardware, we've year by year been able to push this up. So we're at roughly 25,000 servers per technician today, on average across Facebook infrastructure. In Luleå, we've pushed much, much higher than that at times as well. Another thing we look closely is what we call first-time fix. This is how many times we have to go back to the same server to fix the same problem, which we never want to do really. If we can diagnose the actual problem on the first attempt and accurately fix that without having to go back to the server, that obviously saves us a huge amount of time as well. So this one, we've actually been at 100% despite thousands of repairs and lots of people working with this and a complex number of different configurations of hardware and software and so on. We've, for a number of months, actually hit 100% in Luleå and in other data centers as well. We will never ever have to go back to the same server to fix the same problem twice, or because we didn't do the right diagnosis in the beginning and have to go back and do a second round of troubleshooting. And if you compare that to a normal data center where you might pull out keyboard and monitor and try to figure out what's wrong, try a couple of things, didn't work, go back, try something else, didn't work. I mean, you can lose half a day trying to do that. All of that happens in a matter of minutes, and you can't even connect keyboard and monitors to the servers to begin with. With Open Compute, we try to scale away absolutely everything that's not critically needed in a server. So if you think of a normal computer, it's again built, or any server then, it's normally built to be able to do lots of different things depending on what use case it might get. Whereas we know exactly what we're going to use this for. So we can take away all the components not necessarily required, which lowers the energy consumption and increases the efficiency and makes it easier to repair and maintain as well. The only thing we actually put in there that's not strictly required is this little blue LED there. So that one indicates that the server is up and running. You could argue that one might not be totally needed. It looks really cool when you turn off the lights. Another thing we look at is the amount of time it takes to repair a server compared to doing it on normal hardware. Since we all used to run on standard OEM boxes from any of your big manufacturers, we have lots of data that we can compare, sort of apples to apples, between our own Open Compute hardware versus the other OEM servers. And for each area we looked at, Open Compute was vastly better than OEM servers. If you just looked at the actual part swapping, that was 54% faster on Open Compute, which meant that in many cases, the entire repair of one of our servers was quicker than just opening a normal server. Like, we don't even have a lid on our server, so that one's going to be super quick. If you look at handling the ticketing and everything around tooling, that was 80% faster because we could so tightly integrate all of this into our own tooling. And overall, it's about 68% faster doing repairs on the Open Compute hardware versus normal equipment. And I mentioned a little bit on this previously, but we've really then tried to automate repairs as well to a very large degree. And you see these are a little bit outdated numbers, but we at times actually have the majority of the repairs happening completely automatically without human involvement. So if you think of a lot of things that can happen with a server, they might not really require anyone physically going and doing something at all. It might be that the server just hangs, or there's a kernel bug, or it needs a new driver. Lots of different things that you can automatically remedy. So we've automated the repairs of all of that. So what the technicians actually fix is only the things that requires hands-on work at the servers. And we've also really managed to turn up capacity very, very quickly. In Luleå, this is not something we always have to do, but when we turn up a whole new site like we did in Luleå from the beginning, getting everything up and running, like, we need a critical mass of infrastructure to be able to start serving traffic. So there's a bit of a rush to get all of that going. And a whole data hall, which is roughly the size of a football field, then takes us about 1 month to turn up, which, I mean, is thousands of servers, and that's not only getting the servers rolled in, as you see here with a rack being pushed in, it's also provisioning the operating system, getting everything loaded on the servers. So they're actually, I mean, ready to start serving Facebook after a month from the whole data hall being entirely empty. So I think I'm doing quite right on time actually. So that's everything I had in the presentation. If you want to know more about Open Compute in particular, there's tons of information, again, including specifications, drawings, all of this, at opencompute.org. And we of course have a Facebook page for the data center that you can visit to see images and other things that relate to actually operating and running these data centers. And with that, it's open to questions if there's anything you want to know about what we do in the data centers or Facebook's infrastructure.
So we'll pass around the microphone, but I'll actually start by asking a question.
Hi.
So how does a normal day for you look like in Luleå?
For me, or for, I mean, because my days are...
For you, actually.
Oh, okay. That's a really good question. So, I mean, we work a lot with trying to optimize the whole work of turning up capacity and making sure our repair numbers are as good as possible. We have a lot of ongoing maintenances and things like that as well that we need to factor in. So a lot of it is sort of focused around that. And then also, I mean, with a big site like this, we have a lot of ongoing construction work and things like that. So we need to have a lot of coordination of those things as well. So I'm involved in a lot of those things as well. There's no average day, I guess, but roughly that would be sort of some of the main things that would be revolving around. So like, for example, now we are, like each data center's hardware installation has a lifespan of 3 to 4 years maybe, after which you reach a point where the next generation hardware is more efficient from a power point of view than what you currently run. So even if your current hardware is perfectly fine to continue running, it actually pays off to upgrade to the next generation. And that's something that we are currently doing now. So we're in the first building rolling everything out step by step, and then we're going to tear out all the cabling and redo another power infrastructure to adapt the whole building for the next generation network in particular. So I mentioned something earlier called Fabric. Let me just put that slide back here. It makes it a little bit easier to illustrate. It's hard to see, right? But that's an actual schematic of what a Fabric network looks like in a data hall. So Fabric is something we built that allows us to have the same amount of bandwidth and connectivity between any 2 points in the building by building a gigantic mesh network. And that's a completely new network topology and a completely new cable topology as well. So in order to do that, we have to actually rip everything out and start over, which we're in the process of doing now. And the amount, I mean, cabling sounds like a simple enough thing potentially, right? But that's a really, really skilled trade actually. Being a fiber cable technician is something that people train for a long period of time. Like these guys weld together glass fibers in microscopes, and there's about 20 people working full time with cabling alone in Luleå. And each data hall contains about, before Fabric, about 1,000 kilometers of fiber optical cable. And with Fabric, an entire building then contains roughly enough fiber optical cores to go one lap around the world. So that's something that takes some time to get in place as well. And all of those then needs to be spliced and tested and all that. So you see barcodes in each individual fiber to make sure we get the right fiber connected to the right place. And everything is tracked as well in the data center. I mean, we have barcodes on absolutely everything, and we're on a frequent basis, we have to do audits as well. We have to be able to actually find each individual piece in the data center. So they have a random list of assets, and then they want us to basically find and track down a particular one. It has to be in the exact right location. So everything's tracked and scanned as well. So, and yeah, it's those type of topics definitely take up a lot of time.
Thanks for a great presentation. First, how many people do work at Luleå for Facebook, and what's the distribution?
Oh, great question. So with the operational side, we're about 150 people right now. That includes, I mean, it's a little bit more than that, it depends a bit on how we count. And that's everything that's required to run the site. In addition to that, we have lots of people at various stages of construction. I mean, when we peaked with construction during the actual building construction, there was about 350 people working full time at the site, and I think over time there has been about 2,000 people at some point work with the construction of the site as well. So that part alone has been really, really extensive. And with the distribution, I mean, it's I don't have the numbers in my head, but I mean, it's sort of the main skills that we need are related to obviously server and network administration and troubleshooting and engineering around that. Logistics is a big thing. The whole facility operations piece is huge. I mean, we need to be able to rely on our power and cooling systems on a 24/7 basis and be able to maintain and troubleshoot that. Building automation, all that is another big area. Security obviously is critical. Cabling, as I mentioned, is a big amount of people involved with as well, and lots of other sort of smaller functions as well that are required to run the data center. Really sort of try to treat these as autonomous units as well. So we want the data center to be able to function completely separate from the rest of Facebook. So especially for us in Luleå, being 9 hours from our headquarters in California, we can't really wait for them to wake up if we need help with something. So we're really relying on having sort of all these sort of key skills on the site as well.
Everybody's on the payroll, on Facebook payroll?
Not everybody's on Facebook employees. It's a mix between contractors and Facebook employees, depending on what type of role it is.
Are there tours?
Yes. So, I mean, one of the things that is really important to us as a company is being open. Our whole motto for the company is to make the world more open and connected. So we really try to be as open and transparent as possible about what we do. I mean, just showing pictures of our latest generation hardware is something that you probably wouldn't see any other company doing, unless they sell it, which we don't. So we do try to cater for tours as well. We do have limitations to it as well, though, just because of the disruption to work on the site and just the amount of time it takes and all these things as well. But we try to cater for tours to the extent possible. In addition to that, we have a lot of video material as well that we've published that sort of gives you, I mean, a lot of insight into some of the inner workings of the data center as well.
Yes, I have a question about open compute. Has Facebook had any benefit from open sourcing the hardware?
No, I think so, absolutely. I mean, a lot of the stuff is perhaps not immediate, but getting collaboration around a lot of these things means that we can actually start standardizing on common platforms on the hardware side as well. Whereas previously each manufacturer had a completely proprietary solution for doing things. You had a couple of things that were standardized, like the width of a rack and some of the power connections and so on. But a lot of the technology in a traditional data center and the standards associated with it went back to the 1950s even. Like, why is a rack 19 inches wide, for example? Like, there's no sort of logical reason for it today. So getting standardization that sort of translates into what a modern infrastructure requires has been huge for us. And getting critical mass behind this, like as big as our infrastructure is, like that's nothing compared to obviously the entire internet community. So getting others involved has been really critical in that. And I think also we realized that we reached incredible efficiency numbers on our own doing this, but we also saw how much the rest of the industry was struggling with a lot of these things. And with things like the I mean, global warming and anything that, I mean, I think any company can do to try to limit the amount of energy used, I mean, something that absolutely should be done. So by open sourcing this, we can help contribute to that as well, which, I mean, isn't perhaps immediately beneficial to us, but I mean, makes the world better in the end. So.
Yeah. So how do you do the deployment and provisioning of your software stack? And how much time does it take per server, so to speak?
All right, that's a good question. So I don't have any hard numbers on the exact times, but what we do need to be able to do is to provision very, very quickly, right? And do it at a very large scale. So there's actually a couple of really good talks from SRECon, I think not this year, but last year, where some of our engineers talk about the inner workings of some of this. I can share those links and then we can maybe have them posted as well. I mean, in general, we rely on standard open source tooling for pretty much everything we do, and where it's not good enough, we improve it and then open source our changes, of course. So things like the DHCP infrastructure, for example, like that was something that works great on a smaller scale, but I mean, anything when it comes to DHCP servers, was, I mean, more or less not capable of coping with the load of, I mean, thousands of servers trying to request TCP leases at the same time and so on. So, and more critically, we are probably one of the world's largest, if not the largest, IPv6 installation in the world. So we have this massive, massive project running to convert our entire infrastructure to IPv6. And whatever works well on a small or normal scale, it's when you go really big that you start seeing things falling apart. And once that happens, like, there's no one we can go to ask for help, right? Like, we can't Google these things because no one has done it before. So we have to figure out the solutions ourselves. So, so the whole provisioning system really relies on I mean, your standard tools like, I mean, PXE, TCP, and all of that, and then provisioning by having images that are built for each type of hardware. But then that's scaled out on a massive way then to be able to provision lots of servers independent from each other.
So do you use tools like Ansible and things like that are common in industry? Or not really in Facebook because it's just too big?
So I think a lot of the stuff that's sort of more on the, well, we do use some standard configuration management tooling and so on as well. But a lot of it is also tightly coupled with our own internal tools. There's a lot of stuff we've built that's very unique to us, and that, I mean, we'd love to open source it if it made sense to anyone else, but you'd have to have your entire stack to make use of it. So there's a lot of coupling with things like that as well to be able to support that.
Hi, over here. Thanks for the interesting talk. Do you have any tailor-made machine learning hardware, like GPUs that's specifically designed for your systems?
Yes, no, great question. So artificial intelligence research is one of our big areas right now. It was actually a great talk just last week by our CTO at the Web Summit in Lisbon on that particular topic. So we've built, and through Open Compute, open sourced a couple of technologies. The first one we call Big Sur, which is a very, very high density GPU system that allows us to do that type of operation at a massive scale then as well. And we've actually sponsored a number of European universities with that hardware as well to help bolster AI research as well. So.
Thanks for really interesting presentations. Within 5 years, and what does this center you would like to look into, or a little bit expectation on that?
Sorry, say that again. What?
Within 5 years, what you expect is this center is going to grow into, or like what will be the most potentials of this big data center develop into some interesting?
Yeah. That's a great question. So, I mean, in Luleå, we will, I mean, continue to evolve with new hardware generations and so on. So, I mean, that's our main focus really, to try to make sure we can adapt to that and keep growing and scaling. On a global basis, we're also continuing to grow. Like, we're busy building our second European data center outside of Dublin right now. We just a couple of weeks back announced our, would be the 7th Facebook region in Los Lunas in New Mexico, where we're started building a data center a few weeks back then. And I mean, there will be more data center development. We actually announced that we're going to go super big in Texas, where we have a big site as well, and actually build 5 of these buildings there. So I mean, that's another big thing. So I mean, there will be growth like that happening across our infrastructure for sure. And I mean, there's really interesting hardware development as well. I mean, we are always looking for ways to make things, to get more compute out of the same amount of energy used. So, I mean, there's some really interesting development both on the compute side and on the storage and with memory technology and so on. There's some really interesting things happening on the network connectivity side as well, with really high capacity fiber that you can actually run all the way to the server. And I mean, things like that will probably allow us to really start disaggregating the server from the rack as well, which is another big thing, to be able to, instead of having a server that does a lot of different things, you can have sort of your compute and your memory and your storage unit that are sort of disconnect the storage and the server from each other, for example, physically as well. So some of those things will probably start happening to a large degree.
Do we have a final question for you?
How customized is the operating system you're running on there, and can it run anything other than Linux, like XDs, for example?
That's a good question. So, I mean, we obviously heavily customize our own software. I mean, we have several of the kernel developers are actually working for us, and I mean, we're really focusing on trying to optimize that as much as we can, and on an operating system level as well. We really try to do that to a large extent, to be able to streamline things and automate them as well as possible. But this hardware, I mean, you can absolutely run other things on it. People have run Windows on them, and you can definitely run other BSDs and so on. So, I mean, standard hardware really from most factories considered. So there's nothing unique about it in that way. It's just that you can't. I guess you could probably connect a DVD or a USB thumb drive somehow to it, but that's not how we would do it. So it requires a bit of infrastructure around it to provision them and so on. But well, absolutely, you can run anything on them that runs on standard hardware.
I have a final question
Yep.
for me. You mentioned you take cold air from outside. Are there any plans of actually be using the heat from the data centers in the future instead of letting it out in the area?
That's a great question. So, how we actually do this, if I just see, look at this slide again. Most of it are actually recirculates, and I think before we build the data centers, there are all sorts of ideas around I mean, it looked like a rocket engine of hot air coming out of the data center, or there were talks about us affecting the microclimate and things like that. In practice, most of the air year-round really recirculates. During hot summer days, more of it would be exhausted, but it's really low-grade heat. Like the delta between the air going into the data hall and the air leaving it is just a few degrees typically. So there's not a whole amount of actual energy in that you can extract in an easy way. If there was a way of doing it, we would absolutely do it. I mean, that would be a certain. And we do have a series of heat pumps that actually drains energy from this to heat the office part and warehouses and all of that as well. So, but it's so low-grade heat that there's no practical way of actually getting that energy out. I mean, if we would, for example, try to heat the city water, we would actually cool it down significantly rather than heat it. So if someone invents a great way of doing it, we would absolutely do it. But right now, there's no sort of practical way of doing it.
Thank you very much for the presentation.
Oh, thank you.
So next up we have Roman from Sci-Fi Lab, right? Not Sci-Fi Lab, of course. Sci-Life Lab. I'm sorry, I've said that many times.